Okay. Eight up to 32. Okay. In this example, example 2, we have just 5 channels with 5 signals. Each one is of 100 kilohertz bandwidth. But because we, okay, thank you. But because we use now, we don't that because we have to use guard bands. Guard band is some gaps between each one and the other. We don't we need more than 5, because initially you may think that 100 kilohertz into 5 is 500 kilohertz, but actually we will need at least 540 kilohertz. 40 kilohertz, because of the guard bands we have to use 10 kilohertz between each one and the other, and because these are 5 signals, then we need at least 4 gaps between them, 4 guard bands. So we'll use 4 into 10, 40 kilohertz. So it will be like this. We need a link of 540 kilohertz to accommodate all these 5 voice signals. Okay, now, okay, maybe I have to stop for a while here and ask. Oh, the time is going too fast. We are already 44 minutes. So I will just ask quickly here. Is it okay? I know the subject is new and you have no background, but uh, at least you have a good introduction. Then you can review for yourself. Next office hours, we can re-explain all these, or at least the difficult parts. So the concept is new, okay, I know, but at least you have the core idea. So let's go ahead. Okay, no problem. If you want to leave, you can. But okay, I will try. I think Alim will be okay. Dimdim will be clever enough to remember you. In the previous example, how do we know what is required of us? Okay, it's just saying, it's asking just how much frequency, how much bandwidth you need. So you have to calculate 100 into 5 is 500 plus the guard band, because he specified that each signal is 100 kilohertz. Then you have to use a guard bands of 10 kilohertz. So just you know that 5 signals needs 4 guard bands at least. So you will use 500 for the signals themselves, and you will use 40 kilohertz for the guard bands. Then you will need 540 kilohertz. Just that. So okay. Let's now continue maybe. We spent the most of the time, and still we have nearly third of the material. Okay. Analog hierarchy. Usually the companies, telephone companies, use a hierarchy of this multiplexing. Means they don't multiplex once, they multiplex once, then multiplex twice, then multiplex thrice, maybe. So we have, for example, these voice channels of 4 kilohertz, voice signals that will need just 4 kilohertz, because the channel that will take a voice signal, it needs just to be of a wide of a range of 4 kilohertz wide. So they take 12, this number here on the, okay, we are in the slide number 14. I'm sorry, I forgot our friend. 14. So we are talking about analog hierarchy. So the company will take 12, this number on the left, 12 voice channel, and will multiplex them using FDM into one group. This is called group. This is a combination of 12 voice channels. This is called one group because each channel of these 12 channels is 4 kilohertz wide. So this group is 12 into 4. It is 48 kilohertz wide. 12 voice channels. Then this is the first step, but there is still other steps in the hierarchy. So they will group also 5 of these groups and multiplex them using FDM into one supergroup. So this supergroup is 240 kilohertz. This is just 84 kilohertz into 5. Or this is actually 60 voice channels. 60 because here 12 into 5. It's 60 voice channels. Then they will take 10. I am looking at this number also. They will take 10 supergroups and multiplex them using FDM into one master group. And then again, they will take here, I think 5 or 6, yes, 6 master groups, and they will multiplex them into one jumbo group. This is to utilize the lines with very, very high bandwidth. This is usually used in real world. Okay, now we move to TDM. TDM is time division multiplexing. In TDM, we have different approach. So in FDM, if you remember, when we have a figure similar to this one, the displayed one, we had between the multiplexer and demultiplexer, we had 3 channels, but divided this not vertically, horizontally. Means if this is the range, now I am drawing some arrow. If this is the range of frequencies, then we divided the frequencies. Now, no. We are not dividing the frequencies. We are now dividing the time. So we have 4 senders here, 4 devices, computers sending 4 signals. And what we do, we take a signal from one, and this signal from one will use all the frequencies from the lower part up to the upper end, from the lower end up to the upper end. Means that it will use the same, there is no division frequency wise. We are not dividing now the frequency, we are not using frequency division. We take this signal and use the whole range of frequencies, but we don't let this signal take the whole time. We just give it a small portion of the time. Officially we call this a time slot. So we give each signal, just each input signal, just a time slot, which is usually a fraction of what the signal needs. But because the bandwidth is very high, the bit rate, by the way, this is a digital. You can think of this technique in terms of bits and bytes. So we are multiplexing four input signals by giving, means iterating through these four. First taking one input element, one input, they call it one input unit, they call it one input unit. So you divide this, the input here from one, I will draw this. If we consider, okay, if you consider a signal here from one, I am at slide 15, we divide this time-wise, so into units. This is a unit, this is a unit, this is a unit. Then we will take each unit and give it a time slot here. Then go to the, look, you can see my drawings, huh? Then you take from the second, okay, unit, give it here. Iterate through all these four and take a unit, just a small portion of the input, a unit of the input line here, and give it a time slot using all the available frequency. Then when you finish with the fourth one, you go back to the first one and take another unit, put it here. Then the second one, take another unit. So you see in this figure in white color, we have just one frame. Means one frame, one whole cycle. We cycled from 1 to 4, taken one unit from each one. Unit from input 1, a unit from input 2, a unit from input 3, a unit from input 4. This is one frame. Send this. Then the other one, another iteration, another cycle from 1, 2, 3, 4, another frame. This is in pink in the middle. Then the third iteration, 1, 2, 3, 4. This is in yellow. This is a third frame, and send this. So now we are using the whole range of frequencies, but we are giving each signals just a time slot, just a small amount of time. And when I say a unit, means for example, we have this input line here, the first one. I draw now an arrow. Suppose that the first one, for example, we have a byte, means 8 bits. So 001. When I say I take a unit, for example, the unit could be a bit. So I mean take a bit, just a bit, put it here. Then another bit from 2, then from 3, then from 4. And the idea here, because it's not just like that, the idea here is that the duration of the bit from 1, we will shorten this duration. Means if the duration in the bit in these 4 input signals will take, for example, a second, then we'll make it just a quarter of a second. Why? Because we need to to combine each of the four. I will explain like this. If you are just taking an input from 1 and sending this, then from 2 and sending this is just a parallel to serial. But we are doing multiplexing, means we are using a high bandwidth, means high bit rate. So if we are using high bit rate, we can shorten the time, because the bit rate opposite to you can remember the relationship between frequency and duration. If you have a high bit rate, you can have a small duration for each bit. So yeah, you just make the bits of each input short, so you can put many more bits in the same time. I think this will be clear from the next slide. I will see.